to burn, or how people used to observe petrol burning for many, many hundreds or even thousands of years. And I'm going to do this. Now, petrol, of course, is very dangerous. So we have the flammability sign, the toxic sign on it, and we have to take great care when we burn even the tiniest amounts of petrol because it is very, very flammable. And that's, of course, why it's so useful as a fuel. So I'm going to start off here, taking a small quantity of petrol in with my teat pipette here. I'm going to place it onto my fireproof mat, and then I shall set fire to it. Now, once I've set fire to it, I'm going to ask you the question, do you think that this is the way that petrol burns inside a motor car engine? Please watch carefully. I'm about to set it on fire here. Et voila. Now, please look at this flame. Do you think that would make a car do 100 miles an hour down the motorway? No. Just look at the smoke. Yellow, smoky flame. Now, let's look here, children. Wood burning, yellow, smoky flame. You can't see, but it's smoky. Petrol burning, yellow, smoky flame. Candle burning, yellow, smoky flame. Now, to the chemist, that means, and I'm sure you can all agree, there is something similar about. And the similar thing is this. They all contain the element carbon. Carbon is very important. It's what this soot is made of. And I will show you, I can make some of this soot catch here, you see, onto our white surface there. I can wave my white basin here and show you soot collecting there. It is the same element, carbon, which is present in all of these. They have a similarity. You can't dispute that because they're burning in a similar manner. Now, that carbon, of course, is charcoal or soot. And just for your information, candle wax is made up of a mixture of compounds called hydrocarbons. Petrol, too, is a mixture of hydrocarbons, but it has smaller molecules. And wood is actually a carbohydrate. It also is slightly different, but nevertheless very similar in terms of combustion. Now, what I wanted to show you is how the chemist has enabled the fuel petrol to burn much more efficiently, and therefore how it burns inside a motor car engine. Now, for this purpose, I have bought a model of the inside of a motor car engine, and it's a tin can like this. Now, the reason why I've got a tin can like this is because inside the shape of a tin can is a cylinder. Now, inside every single motor car engine in the world, there are shapes like this which are called cylinders. And that is where the petrol burns. That's where the fuel burns. Inside the cylinder is a very tightly fitting piston, which goes up and down inside the cylinder and is connected to a crankshaft which makes the engine go forward. However, I don't have a piston. I have a lid which fits on very tightly. However, for those of you who'd like to know, this is a piston from a real motor car engine. Every single motor car engine, lorry engine, bus, van, whatever burns a fuel, and they're called internal combustion engines, will have these things fitting very tightly inside cylinders, and they go up and down in a reciprocating linear motion, which by the genius of the engineer is converted to rotating motion to make the up and down movement to make things go round, and then the car engine can make the car move forward. So, what I'm going to tell you, that in a motor car engine, of course, the fuel goes in and then is ignited. Now, just for your information, inside a motor car engine and petrol engines, we ignite the fuel with a spark plug, an electric spark. It's like a little miniature electric lightning flash. But in today's experiment, I, of course, will be igniting it with, there's a hole in the bottom here, there's a hole in the bottom there, and I shall be applying my light there. Now, what I wanted to tell you, and this is the key bit of information. If I were to ask you a question now, what is in this tin, you would be perfectly entitled to say, why, there's nothing in this tin because it was full of paint and now it's no longer full of paint. Of course, that's a correct answer. But from the point of view of combustion, from the point of view of burning, it is full of a most important commodity. And that, of course, is all around us. It is air. This tin is full of air, and I am now going to show you how the petrol burns differently when it is allowed to go inside that cylinder. So we're going to now take our petrol here, we're going to take our teat pipette, and we're going to take pretty much the same amount, even that, just literally a few drops of petrol like that, and we're going to squirt them inside there. Now then, what we're going to do is put the lid on tightly, because the piston fits very tightly. There we are. Just make sure it's on properly, because the piston fits very tightly into the cylinder of a motor car engine. And I'm going to now hold this tin for just a few seconds. Now, while I'm holding this tin, the petrol which I put inside as a liquid is undergoing a most important change. But it's not a chemical change. It's not burning. It's not changing into a different substance. It is actually undergoing a change of state. The petrol went in as a liquid, and now, after a minute or so, it has evaporated, and it has turned into a gas, and I will smell it. That smells pretty strong to me, and therefore that means that we shall be ready to conduct our next experiment. That means the petrol has evaporated and turned to a gas, and this is the important bit. It has now become fully mixed with the air. It has formed what we call an homogeneous system. And if we now apply our light to the bottom, please watch carefully and see if you can spot the difference, the color of the flame, or indeed the effect which is achieved when it catches fire. And there you are. As you see, I didn't quite see what happened, but the lid went high into the air. No, please, I am not here. Dear ladies and gentlemen, do you clap every time you drive a car? No, but this is what all your clap. Now, I clap when I drive my cars because I fix them, you see. I drive old baggers and I have great fun driving them. And so I do have a reason to clap, you see, because I fixed it. So if it works, then I'm thrilled to pieces. But you see, inside a motor car engine, this reaction is going on thousands of times in a short space of a few minutes. And that, of course, if you said, can that make a car do 100 miles an hour? Yes, definitely. Now, I don't know, and this is the bit I wanted to tell you, it was chemists who about 300 years ago recognized the hugely important value of air in the way that fuels burn. Now, I don't know whether any of you noticed the color of the flame down there. I noticed it, and I'm sure some of you may have. It was actually blue. Now, that blue flame which you saw is an invention of the science of chemistry. And dear children, the blue flame was invented by none other than the great Robert Wilhelm Bunsen, otherwise known as Bunsen. And here it is in my chemistry set from 1958, is a Bunsen burner. And the genius of the Bunsen burner was the air hole here. The gas went in at the bottom, and it was mixed with air. Such a simple idea, and yet it revolutionized, it played a major role in the Industrial Revolution, because it enabled us to burn fuels more efficiently. Every one of your gas cookers has a blue flame. Every single gas or oil-fired central heating system has a blue flame. All the flames inside every internal combustion engine are blue. And this is the sign of what we call complete combustion. There were very few people who had seen a blue flame before 1850, and none of them survived to tell the tale. And the reason being that they were all miners who were killed in mining accidents. And there were lots of mining accidents, and it was the great Humphrey Davy who used to lecture, who invented the miner's safety lamp. If you can imagine that flame there blowing in your face, the size size of a wall, you are not surprised that no one survived to tell the tale. So what I am telling you today, thanks to the science of chemistry, we have discovered or invented, Robert Bunsen invented the blue flame, which is what we call in chemical terms complete combustion. There is no smoke, no yellowness, the combustion is complete.